Are you ready to step into a world where fractions of a millimeter decide everything? Where chemistry, metallurgy, and physics collide at high velocity? Literally? Every year, over 12 billion rounds of ammunition are crafted. For soldiers, for police, for hunters, for sport shooters. Each one engineered with a level of detail that borders on obsession. This isn't just manufacturing. It's an exact science where pressure, shape, and temperature are dialed in with surgical precision. But what does it take to make something so small, yet so powerful? From raw rolls to rejection or reward, it begins with brass, an alloy of 70% copper and 30% zinc. Massive rolls of it, weighing up to 6,000 pounds, arrive at the factory sealed tight. No oxygen, no rust, no room for error. They're uncoiled and fed into rolling machines. At 600 degrees Fahrenheit, the metal softens just enough to be flattened, shaved to perfection. If it deviates by a hair, it's rejected. Then the press line takes over. 250 strikes a minute, punching out 0.75-inch blanks with machine gun rhythm. These discs are the embryo of a bullet casing. They're heated again, this time to 800 degrees Fahrenheit, soaked in lubricant, and pressed under 100 tons of force. Again and again, each pass elongates and refines the shape until it starts to resemble a casing. But we're far from done. Annealing, controlled stress relief. Every draw stretches the metal thinner, every press molds it tighter. And with each cycle, the brass casing gets a little more tense, like a coiled spring under pressure. Leave it like that, and it'll snap when it matters most. That's why it's annealed. At this stage, the casing isn't just reshaped, it's reconditioned. Heated to nearly 1,000 degrees Fahrenheit, the brass relaxes. Its internal stress melts away, atoms realigning into a more stable form. Think of it as therapy by fire. Then comes the plunge, quenched in water, its structure preserved. But there's still grime left behind. Scale from the heat, lubricant from the presses. That's scrubbed clean in an acid bath, leaving behind only gleaming, battle-ready metal. Now it's time for judgment. Each casing is scanned by lasers so precise that they detect fractions of a micron. Cylindricity, wall thickness, and symmetry all must fall within unforgiving margins. Acoustic sensors tap each casing, listening for the faintest echo of a flaw. If one doesn't sound right, it's done. A microscopic crack could mean a catastrophic failure when fired. The primer, tiny, temperamental, and critical. It's no bigger than a fingernail, but it holds the power to unleash controlled chaos. The primer is the ignition switch. Nestled at the base of every casing, it's a delicate dome of metal filled with explosive compound, typically lead styphnate, though lead-free variants exist for modern applications. But fragility is part of its nature. Too reactive and it could explode during transport or assembly. Too dull, and it won't detonate the gunpowder inside. It's a balancing act, one that's tested with surgical precision before any primer sees a casing. Only the reliable ones pass. Each one is seated into its casing by automated machines. The seating is exact, not a fraction too loose or tight. Then it's crimped, locking it in. It must survive recoil, chambering, and firing without budging. Any looseness could cause a misfire. Any sloppiness, a malfunction. It's the last thing you think about when firing a round, but the first thing that has to work. Loading the bang. Here's where the real chemistry kicks in. Gunpowder, not black powder anymore. Today's formulas are smokeless, stable, and meticulously refined, but they're also incredibly picky. Pistol ammunition often uses spherical grains, tiny balls designed for rapid ignition and consistent burn. The rifle cartridges require more discipline. A 5.56 NATO round, like those used in military rifles, requires around 24 grains. A .45 ACP used in handguns gets a modest 5 to 7. But here's the catch. Even a 1/10 grain deviation is unacceptable. That's how tight the margins are. A single flake too much and chamber pressures skyrocket. Too little and velocity drops, accuracy suffers. Or worse, a bullet gets lodged in the barrel. To measure it all, the machines use optical scales that don't just weigh, they react. Vibrations in the workshop, even foot traffic, are enough to throw them off. And yet they catch it. Every round. Every time. Only once the charge is verified does the casing move forward. The bullet's waiting. Seating the bullet, force meets finesse. Here's the part that seems simple, but isn't. The bullet isn't just dropped in, it's pressed under calibrated force into the casing, perfectly aligned and precisely deepened. This is where weight, balance, and aerodynamics converge. Some bullets are made for speed, others are blunt, designed to expand on impact, maximizing energy transfer. And crimping? That's the final lock. Then comes judgment. Again, but this time it's not just about weight or dimension. A neural network watches every round pass by. It evaluates in milliseconds, scanning for color variance, shadow inconsistencies, and surface anomalies. Anything unusual, even if invisible to the human eye, gets flagged, pulled, rejected. At top-tier factories, fewer than 3 rounds in 1,000 are culled at this stage. That's a rejection rate of less than 0.3%. And for the rest, their journey's nearly complete, packed for war, sport, or survival. Packaging may seem simple. It's not. Bullets are counted, sorted, and packed into batches based on the client's needs. For civilians, shrink-wrapped plastic trays. For militaries, airtight zinc or steel containers are used, marked with manufacturing codes, dates, and even QR tags. Some even have moisture control systems or GPS trackers. One machine alone can package 12,000 bullets per hour. And when demand spikes during war, elections, or crisis, factories run 24/7, 3 shifts a day. A factory you don't just walk into. This isn't your average assembly line. Walk into the primer zone and you'll see it's nothing short of a fortress. Biometric locks, armed security. Robots do the handling. No human touches the powder. The suits are anti-static. Floors are grounded to prevent sparks. Humidity is kept between 40% to 60%, enough to stop dust from igniting. You're probably wondering about explosions. They've happened. In 1998, a US plant went up in flames due to careless storage. 4 people died. Dozens of violations were found, which is why every inch of a bullet factory is designed for one thing above all: safety. The art of metal bending. Enter the press brake. Now let's zoom out from the bullet itself to the massive machines that shape the world around it. One of the most powerful of these is the press brake, a machine designed to bend thick steel with the ease of folding paper. It's used to form car bodies, aircraft components, home appliances, and even military armor. Some press brakes deliver more than 4 million pounds of force. One machine in Cleveland can bend metal thicker than your wrist. In aerospace, even a tiny error can throw off an aircraft's aerodynamics. That's why precision is everything. Computer-controlled press brakes shape aluminum for Teslas, steel plating for tanks, and curved ribs for ships and submarines. Every bend is measured, every angle exactly. There's no room for guesswork. Massive machines, microscopic tolerances. The largest of these behemoths is over 50 feet long. Parts weighing hundreds of tons are lifted by cranes, aligned with laser guidance and welded together. The welding itself is monitored in real time for structural integrity. These machines can stretch, twist, and contour steel into complex geometries. And alongside every press brake is a guillotine, but not the medieval kind. This shear slices through metal like scissors through cloth. With the right blade and gap setting, it delivers a cut so clean it barely needs sanding. When metal meets fire, dangerous precision. Working with gunpowder, molten lead, and razor-sharp steel is not for the untrained. Every person in the bullet factory goes through fire safety drills, evacuation training, and emergency response refreshers every 3 to 6 months. In areas with primer handling or active powder stations, only certified personnel with biometric clearance are allowed entry. Every reject, every cracked casing, or malfunctioning primer is quarantined. Some are recycled, others destroyed in isolated zones. Security isn't an afterthought. It's woven into the walls. From furnace to flight, bullets, aircraft, and the cycle of precision. The technology behind bullet manufacturing doesn't stop with ammo. The same techniques, high-force pressing, precision cutting, and rigorous inspection are used to build aircraft, bend ducts, and shape electronics. Just look at the Airbus factory in Toulouse. Over 11 million square feet, 4 million parts per plane, wings from the UK, engines from the US. Even the cockpit assembly is done separately, like an independent nerve center, then slotted in later. Each A380 is painted with 3,300 pounds of carefully layered paint. Avionics systems are wired like neural networks, all built with machines and methods born from the same philosophy as a single round of ammo: control the uncontrollable. A journey through fire and force. It's easy to overlook the bullet. It's small, it's fast, it's silent, until it's not. But behind every round is a story of fire, metal, chemistry, and calculation. From the casting of lead to the bite of a guillotine blade, from the hiss of acid cleaning a casing to the click of a neural network rejecting the imperfect. Every bullet carries with it the fingerprint of an entire industry. An industry where nothing is guessed, nothing is rushed, nothing is left to chance. Because when a bullet leaves the barrel, there's no taking it back. And everything, every cut, every crimp, every curve has to be perfect.